So the next speaker is Jason Morton, please.
Thank you. Belief propagation in monoidal categories. So an interest that I think I share with a lot of you is some kind of computational category theory where the objects of interest are diagrams. For the purpose of this talk, let's say a diagram is an equivalence class of words, monoidal words, over a finite tensor scheme. Usually with some additional properties x, and by x, closed, compact, or traced, or whatever. And then interpretation is a functor that assigns values. So computational questions that we're interested in for such a diagram, such an equivalence class of words, are computed contraction, solve the word problem, so our two diagrams equivalent, have the same interpretation, or more generally compute a normal form that enables me to do that. Solve an implementability problem, so construct a word using some allowed library of tensors or morphisms, and choose morphisms to approximate some more general diagram. So I'm only really going to talk about one. These other things come up, a lot, and they come especially in kind of the graphical models community that I sort of come from. So it's hard. All these problems are really hard. The contraction is the easiest, well, second easiest one because it's only sharp key hard. These two problems are undecidable in general. So undecidability is kind of a two-edged sword. Right? On the one hand, it means I can't write an algorithm. On the other hand, it means a computer will never put me out of a job. Right? And then this one is at least NP hard. It's probably harder than that. Okay, but these are really important problems for lots of contexts, in probably linguistics, but certainly in graphical models and other things. Obviously, the things that folks in this community are interested in, graphical models, the condensed matter, quantum condensed matter approach, tensor network states, which is pretty popular these days, uses this kind of thing. I've thought about computational complexity, circuits, constraint satisfaction problems, and counting constraint satisfaction problems. Of course, all that can be expressed categorically, and even database problems. So there's lots of tractable special cases people have found, lots of approximate algorithms, and lots of heuristics. So let's try to turn these into algorithms that work for categories, where all I have to do is tell you what the category is, what the axis it satisfies, and I can run the algorithm. Good approach to generic programming. And category theory is good for formalizing analogies, so this is a way to formalize computational analogies. Instead of saying, we're going to write a program that does something like this, it's the same program, just with a different category. Okay, so the example I want to talk about is belief propagation. So this is a message passing algorithm. It's used Perl. And it's used for contraction, tensor contraction, things like partition functions, more generally marginalization problems, and you can do optimization if you work over a tropical algebra, so max plus algebra. It has many extensions. There's lots of analogies, so analogous algorithms that are something like belief propagation, and that's sort of our clue that there should be some sort of categorical algorithm working in there. Among them are survey propagation and turbo coding. People have written papers that show the extent to which these algorithms are really the same thing. So we want to think about what's an abstract version. We can vary the category and get out the algorithm that it runs. So to make that precise, I'm going to describe the setup first. So it's somewhat familiar, but I just want to make clear what I'm thinking about. So there's a tensor scheme. My tensor schemes are finite, also called a monoidal signature. This is the geometry term. This is the one on the here. So this is just a finite set of object variables, including the identity object, a finite set of morphism variables, and domain and codomain functions that assign to each morphism its domain and codomain. Objects. And this can also have relations, so let's ignore that for now, because that adds a lot of complexity. And then from that I can have something called the monoidal language, which is just, I just make all the morphism words that are legal out of these ingredients, and identity morphisms, and that generates a free monoidal category over that. So for every object, the identity morphism is a word. For every f, that f is a word, and given two words, I can take their tensor product, take their monoidal product, and I can compose them if that's legal. All legal ways of putting it together. And I can interpret it to define a morphism in a particular category. Of course, that factors through this free monoidal category, and that imposes some equivalences, such as it doesn't matter whether I tensor first or compose first. And same morphism. And we're going to call this equivalence class of diagrams. So far, we don't have any normal forms for words. Why do we want that? So to do a belief propagation, we need an equality of, we need to solve a word problem. We need to look at equality of morphisms of type I goes to A for every object A. And that's because when we try to generalize these algorithms, we can't check for equality in a set. We can't assume that we're looking at whether two probability distributions are the same. So we have to instead use equality of morphisms like this. These messages are still morphisms, and so now instead of deciding if two vectors are equal up to a variable tolerance, the way you write this, we have to decide on these word problems. Okay, so we need some situation where at least this word problem is easy. We also have to store them efficiently. Word problems in other languages, of course, we can solve some word problems using a coherent graphical language, right? So if we can write it as a graph, we can use that to produce a normal form to solve the word problem. And in fact, that would make the word problem for a free closed category, a free compact closed category, or a finite tensor scheme in log space, so that's pretty good. If we add adjectives, of course, we get the situation that it's undecidable. Even better would be if we had a nice term rewriting system. So I sort of come from the world of Grosvenor bases where you really have that. Here, of course, we don't have anything like that. And a little bit of thought some thought has gone into this, but we really don't have any answers yet. Or it would also be nice to exploit maybe. Another thing you could do is try to use complete to shortcut that. Okay, so for the efficient algorithm, we need to assume that our representation and our word problem for these I-valued points, these morphisms from I to A, are efficient. And in usual belief propagation, of course, we're doing this over a vector space. These are linear transformations, so we just have some notion of the size of the vector space, just the dimension, and that saying that, using that, saying that storage and comparison is linear in size is how we control that growth. Okay, so now let's look at the type of category this belief propagation will work in. The first thing we need is something to play the role of variables. So that's going to be spiders. So let's call a spider category, strict symmetric monoidal category, equipped with some kind of special commutative Frobenius structure. So this paper by the folks here, it was a great paper for me because I sort of came from these two, I grew up with like different mathematicians, some of which thought every vector space had a basis, some of which thought no vector space should be given a basis unnecessarily. And so this sort of idea of Frobenius algebras has really helped me to understand how to reconcile it, what it means to choose basis. And let's call a compact closed category which has spiders, has these Frobenius objects in a compatible way. Let's call it a dungeon category. If someone else knows a better name for this, let me know. So every object has a special commutative Frobenius structure, and any morphisms I construct from the spider and the structure morphisms of the category are equal if they have the same input and output. Same number of wires coming in, same number of wires coming out, the directions they point in. So be bicompatible. This is a good setting for belief propagation because we can bend wires to have inputs and outputs, and spiders play the role of variables. Spiders are variables is the slogan. To translate an algorithm both for graphical models and from algorithm categories. Okay, so what is this algorithm? Basically, the sum product algorithm is just the observation that if a diagram is a tree, we can contract according to the tree. So that's a great algorithm. Lots of people have rediscovered it over the years. If not, you can force it to be a tree using what I know is a junction tree algorithm. It has other names, which also can be extended in the quantum case by just sort of grouping things until it becomes a tree. It depends on the tree width now, the complexity. And you can improve on that abstract tree algorithm using an optimized message passing version, which allows parallelization and other tricks. And this message passing version is what belief propagation is. So in the probabilistic setting, it operates on a factor graph, a bipartite graph. One part discrete random variables, one part factors. I'm thinking of each factor as assigning just a real number, so it's just a positive real value tensor in this setting. And we have messages. The messages in this case are just probability distributions over a vector space of outcomes, spanned by the outcomes. And each factor is just a tensor. And because it's a tensor, I can think of it as a map to one of its wires from all the other wires, right? And that's sort of an important characteristic. We have to be able to reshape things in order to be able to bend wires in order to apply factors. So that means the belief propagation, or the belief propagation algorithm can be described as follows. My second to last slide. A minute left or so. At the variables, I compute the Hadamard product, the pointwise product of the incoming messages, and I output it as the outgoing message. Now, in a probabilistic category, the Hadamard product is going to include a rescaling. That's part of the belief propagation algorithm. So I have a variable. I take the Hadamard product of the inputs, spit out the output. At the factors, which I'm going to draw as a box, I compute the tensor product of the inputs, apply the factor, and spit out the output. So the resulting algorithm is a bunch of equations that say all of these messages are the same at each time step. So I gave you an update rule. You can repeat until convergence. You can use the uniform distributions for the initial messages. So those are going to be the units in the Frobenius algebra that corresponds to probabilistic case. And in the tree factor graph, you're done in 2 passes. Leaves to the root, root to the leaves, and it's exact entries. So now for the categorical version, well, it's just the same thing. Now that we've set it up this way, we apply this, shut this spider to the incoming messages, output the result. If there are no incoming messages, we just treat the spider as a unit, so we plug a unit onto it. At the factors, we compute the product of the incoming messages, apply the F, and output the resulting message. And we get a system of belief propagations, which are just equalities of I-valued points. And they describe the fixed points. We have to be able to resolve that word problem in order to do it, but okay. And again, the initial messages are now just units instead of probability distributions, and the nice behavior of the tree is preserved. And you can make it a little bit more general by saying, you get rid of the spiders and just use another factor. This was just a special kind of factor. That's about it. So the theme, again, is to say, I'd like to see a future in which, so, I heard from Bob that he feels that the United States is a no-go area for applied category theory. And of course, the question I always get is, well, what is it good for? What can we do now? Having just rephrased the problem. So this is one answer, this sort of theme, which is to say that probably once people were similarly had this problem with, why did you bother phrasing your computation in terms of matrices? I know what to do entry-wise. So it helps to organize things that way. And I think since there's such a broad universal problem set of giving categorical interpretations, if we have a way to think about algorithms, that once I tell you what the category is, the algorithm is done, and maybe it could be a nice abstraction for people who do applied math. Thanks.
So, in your definition of Gaussian category, you didn't seem to make reference to collectors of spiders. In the bottom part.
But here's the spider.
Yeah.
Each
I
output.
mean, the sort of coherence part in the bottom. You don't make any connection if you've got a diagram, so when you contract, you need to consider the separate parts, right? I didn't see any reference to that aspect.
Separate.
I mean, if the spiders are not connected, then they don't contract.
Yeah, that's if there was just 2 spiders with the same object somewhere at different places in the diagram. Yeah, we don't.
Because that so you could have things with the same inputs and the same outputs, which are not equal.
Well, the morphism would be equal. So this is basically just the Frobenius. I'm just saying that no matter how I construct, it, it's just the spider spoke there with TQFT.
Yeah, that's only,
But with arrows, pointing arrows.
that's only if everything is connected. If you got 2 separate components, that's not what we say.
I think I don't quite understand.
Okay, Jamie, but what I'm confused about is that point 1 here implies point 2. Why have you put point 2 as a separate condition?
Well, there's some sort of compatibility. I think you could each object can have a special commutative Frobenius structure that was not necessarily compatible with the dual structure.
Right.
It's hard to imagine a situation like that, but it's possible.
I propose that you take definition offline. Discussion about this definition offline. So let's thank the speaker again.